periodic table is instantly recognizable. It's not just in every chemistry lab worldwide, it's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon, it's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitri Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really, that had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitri was making a bold statement. He said, and I'm paraphrasing here, "Y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum, Eka being Sanskrit for one." Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time: scandium, germanium, rhenium. The element he called Eka-manganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitri predicted its existence, 30 years after he died. Dmitri died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitri Mendeleev, the architect of the periodic table, will be staring back.
So that video specifically mentions a metal, gallium, with a ridiculously low melting point that Mendeleev's time didn't know about. But we have some. Let's see what happens when we make a spoon out of gallium and then just put it into some lukewarm water. It's got a very low melting point. Let's see what happens. And so here is our gallium spoon, which is 100% solid. it's important to note that this water is not boiling. It's just warm. That's my finger. Gallium has a melting point of 85 degrees Fahrenheit. That's about 27 degrees Celsius. Extremely low melting point for a metal. And nothing left of our gallium spoon but a puddle. So, after quite a lot of time spent looking at this thing, hopefully it is starting to become evident that there is a logic to how this is laid out. And by now, hopefully, you have noticed that everything that is in column 1 has an electron configuration that ends in S1, and the row that it's in tells us what energy level it's in. That means that there is a connection. Everything that is in group 2 ends in S2. If we skip over to the other side of the periodic table, everything that is in this side is going to end in something P. And by the time we get to the noble gases, everything ends in P6. So there is this neat arrangement where we can refer to everything that's in this part of the periodic table. We'll call this the S block, because everything that's in here ends in something S. Everything that is over here on this side of the periodic table, we're going to call this, let me make that bigger, we'll call this side the P block. If you've been paying extra attention, you know that everything that is in this middle section ends in something D. And these get a little weird. And so you might have heard that this area is termed what we call the transition metals. And we'll get into that more in chapter 6. But for right now, we can simply refer to this as the D block because it is filling D orbitals, right? Everything that's in this column is D1, D2, D3, D4, D5, D6, D7, D8, D9, and D10. And that leaves us lastly with this section. What we hopefully have noticed is an area that is filling up F orbitals. And so we'll call this the F block. And it really belongs here. But if we tried to put that here, the periodic table wouldn't fit very nicely on my screen. And so we'll leave it down there just like it is. So we're going to be exploring the layout and its more general reactivity aspects. But hopefully what we're going to explore as this chapter goes further is that, if you remember way back in the beginning when we explored what happens to the alkali metals, starting here with lithium, sodium, potassium, rubidium, cesium, and francium, hopefully you remember that as our metals moved down the periodic table, the explosions grew more and more severe and more dramatic. That is a measure of something that we're going to call reactivity. And reactivity for metals, let's remember that this side of the periodic table, let me get a different color here, that this side of the periodic table is what we call the metals up until this flight of stairs. And that on the other side of the periodic table is what we call the nonmetals on the other side of this flight of stairs. And so the reactivity of metals has a tendency to increase as we go down. We see that as we approach francium. We're also going to find that metal reactivity has a tendency to increase as we move this way. And the way we know this is because metals near the middle of the periodic table, especially elements like gold and silver, which being near the middle of the periodic table don't really react at all, which is why they're worth so much. And that elements, as we move towards the outer edge to the left side of the periodic table, tend to be more reactive. And the same is true with elements in the non-metal section, and we're going to be doing an experiment with our friends, the halogens, fluorine, chlorine, bromine, iodine, astatine. We're going to find out that it works exactly the opposite with halogens and nonmetals, and that is that their reactivity tends to increase as we move to the upper right corner. We'll be doing some experiments to evaluate the reactivity of halogens. We'll find that fluorine is the more reactive. So let's practice this a little bit, being able to identify roughly what an electron configuration is just by where an element is in the periodic table, and trying to use its location to predict its relative reactivity. And we could say that as we move this way towards the bottom left corner, and as we move this way towards the upper right corner, reactivity increases. So let's practice, all right? See you on the next one.